Hi, I'm Ken Perlin. I'm a professor at NYU, computer science, and I am here to talk about the future. The great thing about talking about the future is nobody knows whether you're right or not, so you can pretty much say anything. But if I'm wrong, like 25 years from now, I'm wrong, then you can come up to me in 25 years and I will buy you a beer. So that's my guarantee. So for me, the future started very early, ironically, with a kind of nod to the past. When I was 5 years old, my brother Mark was 7. We used to play with little plastic dinosaurs in the basement in my parents' house in the Bronx in New York. And by the way, I'm wondering, can the lights here go down a little bit? Because everything's going to be on here. So.
But if it goes down, we can't see you. That's the problem.
I see. Okay. All right. Okay. So, the thing about dinosaurs. How many people had dinosaurs when they were kids? Wow, that's amazing. The thing about them is that if you give plastic dinosaurs, in this case they're from the Marx Plastics Company. I think they started making them in 1963 or something. You give them to a little kid, and the little kid will spend hours. Like, they'll just tell stories. There's the T-Rex, and there's the Brontosaurus. And my favorite was the Brontosaurus, because I learned at some point that apparently at the time when I was a kid, they believed that it had been a mistake and there had been no Brontosaurus. So they'd made this plastic dinosaur that was supposed to be the biggest dinosaur ever, and then it turned out that it didn't exist. And my heart went out to it. It was like it was more extinct than the others. And so I just really liked it. But the thing is, you take these things and you watch, and I hand once to my nephews. And my little nephew Jack, he would just like run around the corner, and he would like tell stories and romances and fights and adventures, and they go on adventures. And what you realize, little kids do not think like us. They don't think linearly. They don't think logically. Instead, they're just telling stories in their head all the time. They're just these story generators. So I think that what's really going on with everything that people do with computer graphics, with architecture, with art is, I think what's happening is when we're little kids, we have this superpower. And then you get to about 8 years old or something, you get your adult mind, you start thinking rationally about things, and you lose that superpower. And you want it. You want it back. You can't, like the little kid watch the same Disney movie 100 times over and enjoy it every time. But you want to be able to have that feeling of magic. And so I think what we do is we use our adult intelligence to create these prosthetics. And it's basically a prosthetic for the mind, so we can go back into the state that we've lost. And in this sort of creating visions of the future, I mean, you're probably aware that going back science fiction, 1957, Forbidden Planet, and in books go back and back and back to Jules Verne and earlier, people creating these alternate worlds. But in the actual world of engineers trying to physically make alternate reality, probably the most significant first step, there are a lot of them, but the most significant one was probably 1968 when Ivan Sutherland created the first virtual reality headset. It was called the Sword of Damocles because the actual apparatus was huge, and if it ever broke, it would just kill you, which kind of made it edgy, I guess. But that's what you could do then. And then as technology evolved, people gradually started streamlining these. So this is VR from VPL, Jaron Lanier's company. This is from exactly 30 years ago. This picture was taken in 1986. And it was too early. It's interesting because the technology does not seem dated, but that guy's jacket is really not keeping up with the times. But the gloves, the goggles, it all kind of still works today. This is 30-year-old technology. It was originally developed for the U.S. Space Agency, and then Jaron adopted some of those things, added some other things. And interestingly, this is just last year. So this is the Vive. You guys have a Vive here, I think. I have some demos from our lab, which we're going to be able to load and play with tomorrow. And it doesn't look a lot different from 30 years ago. It's still kind of clunky. The worst thing about it is that big wire trailing down the guy's back. Those of you who know the Vive know that it's really high quality. It's amazing. They're the real modern innovatives, Valve and HTC, in virtual reality. But it's not something that would be part of your everyday life. Gear VR 2 years ago, 2.5 years ago, and now Google Daydream, they're streamlining things, but the problem there is that, they're basically just working with phones, and in fact with this phone, Galaxy Note 4, and the problem with these is they're a little less bulky. You still wouldn't want to walk around like this all day, just covering your face, and separating you from other people, but also they only do orientation. They're not what's called room scale. The Vive and its competitors are room scale, which means you physically walk around and you can see the world walk around with you, and people in virtual reality can also track your head movement, which doesn't happen with Gear VRs and Daydreams. Now, meanwhile, there's these parallel developments. There's the augmented reality glasses. There are various kinds of augmented reality glasses, and they look really cool. Some of you may have tried the HoloLens, I don't know. But one of the problems is that the limitations of power, of optics, of all kinds of things means that the field of view of these things is really tiny. They're actually only presenting a 30-degree insert, which means you never get a sense of immersion. You just get a sense of and at some point, people started complaining to Microsoft because their ads for the HoloLens made it seem like people were just surrounded by stuff. But actually, it's just a little tiny thing. It's still really cool, but it doesn't, it's not plastic dinosaurs cool. But that's going to change. Sometime people are already working on technologies now. Sometime in the next 5 or 10 years, there's companies like Magic Leap, and there are things going on at all the big players, Google, everywhere, where it's going to kind of look like this. It's going to just be like these glasses that you put on. And I want to make an observation here, which is unless you actually look around, you can't remember who sitting next to you is wearing glasses. Which means that glasses are an incredibly effective technology because we forget that they're a technology. We just accept that, this person sees better. If I think about it, I don't even know, are they nearsighted, are they farsighted, whatever, it doesn't matter. The important point is that you see the person, not the technology. And what's going to happen once this stuff starts getting, and they'll have these tiny little micro displays, instead of this big thing which was meant for this, being adapted for this, and this is merely a transition technology for wearables, you're going to have tiny little 6K by 6K displays, with a little projector, and it's going to be projecting, there's going to be some light pipe or something, and it's all just going to be, it may not look exactly like a fashion reject from Tron, but it's going to be something that people don't think about. It'll just be part of just the way when you meet somebody, you don't react when they take their phone out of their pocket and say, wow, you have like a supercomputer from Star Trek in your pocket. No, it's just the phone in their pocket. In fact, you kind of get surprised if people don't carry on their phone. So it gradually makes itself invisible. And I think that this is going to be crucial, because what's going to happen once we get there is that we will finally be entering what I think of as the age of computer graphics. We're not in the age of computer graphics. Computer graphics is still something I see here, or maybe I see a little thing on my wrist or something, or I put this thing on and I check out of the world because I'm not in the world anymore, I'm in this other place. But once everywhere you look, you can have computer graphics, and it's all tracked, and it's all, and the system somehow knows where you are, and it all becomes inside-out tracking. In other words, the thing you're wearing kind of does all the computation. Then you can go anywhere in the world, and at that point, what you see and what other people see, you'll accept that the virtual and the real are connected. I chose this picture because this is obviously a fake object because of the lighting, et cetera, and the lack of shadows, but we will just accept that that's part of the world, just as earlier forms of virtual reality we accept as part of the world. I mean, the first virtual reality were the cave paintings right here in France. And as far as we know, there may have been earlier things, but those lasted. And those were 30-something thousand years ago. And why do I say they're virtual reality? Because people just decided to create a representation of something that didn't exist in the world. And the reason that people did that, I think, is tied to the real superpower that humans have, which is language. The fact that we actually go around reading each other's minds. I talk, sound comes out here, you hear it. I say the word elephant, and ideas about elephants show up in your head. And we take this so for granted. We just forget just how amazing this is that we have this adaptation as a species. And this is not technology. This is actually a natural adaptation. But all of our technology is built on the fact that we just send ideas back and forth to other humans and receive them and don't think about it. And therefore, we try to create representations of those in the world. And in some sense, in a broad sense, that's all virtual reality. When you go to a restaurant and you pick up the menu and you both order off the menu, you and your friend, you're not thinking about it, but you're basically doing something that's an earlier version of this or even of this, which is there's nothing there except in our minds. You can't taste it, you can't touch it, you can't smell it, you can't feel it. It's just a piece of paper with scribbles on it. And yet we accept that there's information there because our minds can receive it, construct it, communicate it to each other. And all of this is a small step, in some sense, from the cave paintings. The really big step was the evolution of language in humans. And now, as computers get faster, we just deploy it in different ways. And I think it's all basically this approximation to what can we do as grown-ups? What's our next version of little plastic dinosaurs? So, for example, for me, this is interesting, but this is really interesting. I don't care about high-quality rendering. I care about, oh, I put my hand out and there's a creature, and it's looking at me, and there's interaction, because I'm really interested in animation and the idea of bringing things to life, and not. Again, it's not about the graphics, and it's not even about whether we're interested in these creatures. In some sense, for me, it's whether they're interested in us. It's that two-way thing that you can't get from linear media that I think draws me to this. And always in my career, from the very beginning, when I started in computer graphics, I think when I made this, I think I was probably younger than almost anyone in the room here, but it was stuck on a screen. I wanted to create visions, like something, and this is a scene from an animation, so it's like almost like a Magritte comes to life. But I wanted it to be here, and that's going to happen in the next 5 or 10 years. And then it's going to engage our social selves in a very different way. And once these little kids start seeing this, pretty amazing things are going to happen. Now, I think the most amazing thing that's going to happen is I started this talk by talking about little kids. They're not like us. They're not like us in many ways. What's going on in this mind, there's stuff that's going on in this mind that is not at all going on in our minds. At around the age of 2, kids are learning vocabulary at an impossible rate, a rate that no grown-up could ever learn it. They're learning new forms of syntax, they're learning ideas, they're absorbing, they're just these learning machines. They have actually different brain structures that then gradually go away between the ages of 6 and 8 and get replaced by different brain structures. So I think once little kids can do this, and that becomes integrated into their language, that we see stuff right in the air between us, that's going to be the big step. It's not the supporting technology. Book printing is interesting, but novels are essential. There's a difference. And I think it's that level above the enabling technology and what the next generation that takes it for granted makes with it, which is really the good stuff. Like, what will these conversations be like in the future when they're talking about stuff that's language to them, but not language to us, because we'll never be native speakers of whatever that future evolved language is, but we can help pave the way. So we've been doing a number of experiments at NYU with virtual reality. And they changed a lot after the Gear VR came out. We had been trying to fake things in different ways, but when I first saw the Gear VR, my friend Mike Woods, who worked at Framestore in New York, showed me a demo in September 2014, and I had tried the Vive. I'd gone out to Valve, and I had done the Vive demo in May, and so I realized, oh, this is exciting, this is coming. But I didn't find it interesting in the sense that it wasn't part of social engagement, because it had this big wire trailing, because you had to have a PC, a high-end PC for every user. But as soon as I put on the Gear VR, and it was only orientation tracking, so I could only do this, I couldn't move around. My very first thought is, hey, I'm a professor, I'm at a university, I'm going to go out and buy a motion capture stage. So I put these markers on it. I put it in a MOCAP room. So we bought a MOCAP room. It cost about $50,000. You too can do this if you have $50,000 of somebody else's money to spend. And we basically had people walking around, and this is actually our conference room in our lab, because we started putting different MOCAP. Now we have about 4 or 5 of these MOCAP labs sprinkled around the university, and they all communicate with each other. And since we went through the process of doing it, buying the OptiTracks, we could then tell the other faculty, oh, you should do this, you should buy this, and they're really cool. Each of these cameras costs about $2,000. There are 16 of them in this particular room, but the advantage of it is if you can get your graphics running on a phone, then you can run, say, something like Unity, or a game engine, which a lot of people know how to develop for. I mean, the nice thing about something like Unity is it's not just for computer scientists. You also have artists and animators and various other kind of creators. It creates this production pipeline so people can collaborate. And the VR is really running on everybody's phone. Everybody's running the same game. And the little tracking markers are being picked up, and they're telling the position and orientation of everybody's head. We can also strap markers on wrists and ankles to give full body, and then we sort of build fake bodies for people. And so you're in a physical space. You're seeing people in the same physical space. The sound is really coming from their mouth. You can reach out and you can touch them, except you visually transform the space. Technically, what's going on is that a Wi-Fi network is sending the positions and orientations to the little game engine running in everybody just, I am the camera for me, you are the camera for you, but we're seeing the same game world. You can pick up objects that are tracked, physical objects, and hand them to each other. So we started doing this about 2.5 years ago, and it's kind of virtual reality, but it's not exactly virtual reality because of this physical co-presence, more like a holodeck from Star Trek. And so we started calling it future reality, because in the future, people won't even think about it. They'll put on their glasses and they'll be able to see whatever they want. And those of you who are science fiction fans may recognize this scenario from some books. For example, a 2005 book by Vernor Vinge, Rainbow's End, where he sets it the convenient 25 years in the future, because everything happens 25 years later, as we know, in science fiction. And everyone in the morning puts on their contact lenses, and they just walk around and see whatever they want. And he explores not how it works, because that's just how it works. That's the plumbing. But how does it change people's lives? What are the new challenges once I can look at you and see a completely virtual version of you, and stuff floats in the air between us? And somebody can kind of beam in from California to join us, but it's not going to be the same because he's physically present and they're not, and it's always going to be a little bit different, but we can start having this emotional engagement with each other. Because actually my motto that I somewhere along the line in this last 2.5 years, I combined two of my heroes, Gene Roddenberry and Jean-Paul Sartre, and I decided that our motto was going to be the holodeck is other people. And I think it's more positive than Sartre. I think he was darker about it. But the point is that, how many people know who both of those people are? Okay, all right, good, all right, okay. I was curious. So the key is that the only thing people care about really the only thing people care about is other people. In some sense, you could think of like the way our minds work. It's kind of like this is our view of the universe. You know, it's just this, oh, there's a building, oh, there's a river, there's a mountain, whatever. And then there's like, oh, there's a person, you know, and there's another person. And to each other, we're kind of like these big spikes of interest. We totally focus on each other. And basically everything we do, those cave paintings are one example. This talk, I'm giving another example. Everything we do is trying to burrow like a line between my brain and your brain. That's all we care about as humans. It's what our brains are constructed for, is social engagement. And we're good at it. And we get better and better at it. And we use any tool we can to engage in social. And even people who are total misanthropists couldn't live without other people. It's just the way we are constructed. So we did a bunch of experiments, and I'm going to show you some videos of these social experiences that we created. And then I'm going to talk about, first I'll talk about that, and then I'm going to talk about my own thoughts and the little group I've been working with at NYU on how do we evolve that visual language that's going to come next once all this stuff becomes a reality. So let's see. This was something we first showed at the SIGGRAPH conference in 2015 in Los Angeles, but then we kept making different versions of it. This particular one was last year at the FMX conference at Stuttgart. We call this Hallo Jam, and the idea here is that you put people in headset, you track their wrists and their ankles, and that's enough for us to build computer graphic bodies using a technique called inverse kinematics. And they see each other as virtual representations, and they can all draw in the air socially, collaboratively. And it's really not about the drawing in the air, it's about the collaboratively. And they start making up games, they start doing things that we never thought that they would do. People started dancing together. It was really cool because they see the other person and their mind says, that's my friend is wearing a digital costume. So it's still them and it's still the person they came in with, but they've just entered an alternate reality. Interestingly enough, during this conference, because of the size of the space, we could accommodate lots and lots of people. Because of the size of the space, we could only fit 3 people because that's how much room they had at this. And so each of them had a little wand that was, let's see, how do I do this? Escape, there you go. Yeah, each of them had a little wand that they would draw with. And something interesting and unexpected, we'd been doing this for about almost 2 years before this conference happened, and then one of the wands stopped working, and because we were all the way over in Germany, we didn't have a spare. It's just a little button press because we were using this old technology. We were using Wiimotes at the time. And so suddenly we had 3 people in the room and only 2 wands to draw with, and we were really kind of like, uh-oh, people are gonna have a really bad time. Turns out it was the best design decision we ever didn't make. Because once you have 3 people and 2 wands, now everybody's engaged with everybody else. They start sharing them back and forth. They start negotiating, like I get to draw this and then you get to draw that. And it increases the focus on the other people. And the more you increase the focus on the other people, the better time people have. So it was this weird less is more that we can't take credit for it. It was actually just a bad Wiimote that gets the credit for being brilliant. But that was an important lesson. The holodeck really is other people. So then we decided in the US, everybody celebrates Halloween, and that's boring. So we decided not to do the obvious and do VR and Halloween. We went 1 day later and we did an experience of the Mexican Day of the Dead, which is actually a happy day because it's the day that the spirits all celebrate and have parades and everything and celebrate because the living people remember them. And so it's kind of nice, it's kind of joyous, nobody walking around with scary, Donald Trump masks or anything. All right, that's the last political reference I'll make. Let's see, so where was it? Oh yes, Dia de los Holos. And we had several hundred people come through, and here we went more minimal. Instead of strapping on wrist and ankle markers, we just said, here, put on the headset and give you 2 wands. And then that way people could just go into the space. So we had these very minimal avatars, which didn't seem to bother people at all. Mostly they were, and remember, this is all running on these phones. So mostly they were just like really like the cool dancing skeletons, and they were in the middle of a parade float, and they could engage and play games and interact with creatures. So here's a little video we made to show this. The fan that you see looks like an object that people can walk up to. We track that also. So things blow air in your face and stuff. So, yay, that was great. And that was a complete success. We really, but then we decided we wanted to keep pushing it further. So the next thing we did, was the most recent thing we've done, was, so the artist who is like our kind of artist in residence who designs all these pieces, his name is David Lobser, and he's just this really brilliant animator who had never really programmed before, and then he took my graduate computer graphics class, which was crazy. But then once he got past the, oh, I can program now, he started doing amazing things in the class, and I said, we should work together. So like we've continued to work together for the last 2.5 years. He thought, why don't we go even more minimal and just give people headsets, just headsets. Let's forget about the arms, have people come up with a scenario where people can interact socially as creatures where it's just their heads. And so he came up with this vision where we are all a flock of birds, and you see the other people as birds, and you see them in this like wonderful forced perspective, so that once you put the headset on, even though in reality you're just in a modest-sized room, you feel like you're in a vast space and you're all flying around incredibly fast, and birds are flitting all around you, and you're in a nest, and he has a very unique way of looking at things. Like the activity is eating bugs, but the bugs are these beautiful multicolored bugs that look like they're like from some drug trip. Not that I would know, And this is really cool because it allows a lot of people to participate. This experience, I could support like 30-something people at the same time, which I'm realizing, from 2026, I'm saying, well, 30 people at the same time. In 10 years, people think that's nothing, but it's like really cool because you can get that many people in a room together simultaneously. So this is the beginning of like going from the Nickelodeon to everybody sitting in a theater. This, like, for this medium, like, we're starting to push those limits and have lots of people able to go into a world together. And so I'll show you Flock. Okay. Let's see, there it is. Show this at the Future of Storytelling festival about 2 months ago. And there were 700 and something people that weekend at the festival, and all of them got to experience it. We also strap these feathers on you. The feathers are actually not tracked, but people really like them. That's what people look like to each other. Those are the cool bugs. Now, as you walk into the bugs, you kind of eat them, and as you eat them, you start getting more interesting music and more interesting experiences. So there is a kind of a game-like quality to it. Some people just raced around, other people went really slowly. And I think this is one of those experiences where you really do have to be completely immersed in it, like all of your peripheral vision, so that you really feel like you're in another place. By the way, it does no good at all to open your mouth while eating the bugs, but people like doing that. All right, yeah, we don't have to hear the interviews, but okay. Yeah, so that gives you a sense, and then what happened there is that we are now down to really just, so I'm going to talk about this now. This thing that you just saw was a dictionary. I wanted to show you a little behind the scenes, because what we're trying to do next is we're trying to build that language. And I'll go back to that dictionary. And once we have that language, this is the world that I think we're going to have. We're basically going to live in a world that kids will take for granted, but we will think of it, I think, as Harry Potter meets Harold and the Purple Crayon. And it'll just become, and it'll be nice because it'll be a powerful world, but it'll be kind of bittersweet because children won't even realize they're living in a world of magic, like little kids don't realize that this is a world of magic that was, you know, in Star Trek 50 years ago, exactly 50 years ago, this was seen as, oh, in the 23rd century, people have these things. And now, of course, kids just always had them their whole lives. So, you know, another thing, kind of a sad saying that I have is that the future lasts for about 5 minutes. You know, it's like, oh, wow, that's the most amazing thing. And then people just like, oh, where's my cell phone? You know. So I've been developing this system with some of my students that we've been building and building and building a vocabulary so that we can actually, you know, when you draw things, the idea basically is that when you draw things, the computer knows something about what you drew, and therefore the thing you drew can kind of come to life and have behavior. And so, for example, if I'm trying to teach about pendulums, I might say, hey, a pendulum swings, but I can also bring up another object, which is kind of an information object. So I can say, oh, the pendulum is swinging, and I can explain to people, you know, when you change the length of the pendulum, you change its frequency, et cetera, et cetera. And this kind of way of discussing things is, I think has been really helpful to me teaching. For example, I teach computer graphics, and in my teaching of computer graphics, it's if you just draw on a blackboard, it just sits there. If you just bring up a computer program, well, now you're just running a computer program. They could be looking at that on their phone. But if you combine the narrative with the subject matter, then you can really act more effectively as a teacher. For example, my own stuff, stuff I did many, many years ago was develop this whole idea of procedural textures. And so I can actually show them procedural textures. And but by the way, the fact this is all running in a web browser makes it much easier because it can run on phones. We can transfer it to our VR experiences. It kind of doesn't matter where you are. It's all HTML5. This is all JavaScript. And how many people here are graphics programmers? So you'll appreciate that, like, there's JavaScript, but then the really cool stuff happens down in the shader languages, because now in the last 4 years, they now give you access to the hardware, so you can start writing your own fragment shaders. And basically, your computer has within it a graphics supercomputer. And until recently, you didn't have access to that as a programmer. But in the last few years, something like this, when I first started developing the techniques, noise and turbulence-based techniques, it could take an hour to compute something like this. This is all happening in real time on a dinky little computer. And the reason it's happening in real time is that I actually have access to programming at every vertex of every triangle. I have access to every pixel. And this thing is called a fragment shader. This is actually the code that is describing that being a planet. That's actually not a planet. It's really actually totally fake. It's actually a square. See, it's totally flat, and it's just a texture. But at every pixel, I'm running this program, and you're seeing all the code except for something called a noise and turbulence functions, which I developed a long time ago, and I just implemented them to run in the hardware, in the graphics processor, which means that I can be making real-time designing decisions, like I can change the color of things, or I can change the shape of things, and literally every bit of information, except for the implementation of the turbulence itself, that makes this into this planet, like the atmosphere, the motion, everything, is in those lines of code. These shaders are incredibly powerful and incredibly fast, hundreds of times faster than the CPU in your computer. So the ability to take people through difficult topics like that by actually just putting it up there is actually really, really important. But I want to talk a little bit about the future and then circle back to the teaching, because I want to make sure that we really understand what we're talking about here. One of the things that can happen in so let me just actually put a little thought in your head. This is Jianyi. Jianyi, she's one of our PhD students. And what she's doing now, as you can see, is her hand is being tracked, and this little toy robot is being tracked. And she's telling it to come toward her by gesturing, and the robot, and of course, it's all being motion tracked. And in the future, you won't need the OptiTracks. In the future, when computers are much faster, there'll be some really, really inexpensive thing that's probably going to be worn or hung on the wall or something that will be everywhere, that knows exactly where her fingers are, knows exactly where the robot is, et cetera. But so this idea, which Werner Vinge does talk about in Rainbow's End, is that if we're wearing those glasses, well, one superpower is that we can see things that aren't there, which will just seem perfectly normal. But another superpower, and it won't seem like a superpower, it'll seem normal, is that we can also choose not to see things that are there. Now, we do this all the time. There's electricity here, and there's wires running through the walls, and when you go into the kitchen and you turn on the tap, there's plumbing. There's all kinds of technology that we choose to hide because we're not interested in the infrastructure. We know it's there, but we're not interested in it. Well, once we wear these glasses, there'll be lots of little robots running around bringing us stuff, and we won't ever see them, because why would we see them? So I'll just want that glass, and I'll point to that glass, and the glass will just come across the room, and I'll get it. And actually, a robot brought it, but it's part of the plumbing. So if you start thinking this way, then you start thinking about how people interact with things, then things that we now think of as magic will be perfectly ordinary. So for example, using my Chalk Talk language, we call it Chalk Talk because it's kind of like drawing with chalk. This is in Chalk Talk. I showed you that dictionary at the beginning. This is the dictionary word, it's a pictogram, for I'm going to draw something as though I made it on a clay potter's wheel. So now all I need to do is provide my own kind of final stroke to this, and it built that. And it built that, of course, in computer graphics in the computer. Now, I might be having a conversation with Jesse, and I'm saying, I was thinking about designing this thing, and I draw this, and then he says, oh, but what material should it be? And I should be able to just, bring up some list of material properties, like this particular color or something, and just drop that on there. And then Jesse and I can go out to lunch. And while we're out at lunch, now remember, this is sitting on the table because this is the future, and I drew that right here. And while we're out at lunch, the 3D printer starts running, and the robot takes it and puts it there. And we know that, oh, well, it's there, but we can't touch it yet, but it's already in our world, just as that gumball machine was. But when we come back from lunch, we'll be able to pick it up. Like, oh, it's a little too heavy, and maybe make some changes or whatever. And that will be normal. But meanwhile, it's a conversation. And things that we now think of as, oh, I have to go and do this by myself and then come back and talk to you about it, will be able to be part of the conversation. Now, we have this concept that is very well understood in human interaction between stuff which is compositional and stuff which is conversational. When I go and write a symphony, I just need everybody to leave the room, and I sit there and I scribble, or maybe I work on my iPad and I come back months later and here's my symphony, and then people play it. And similarly, when I write a novel, I go into my room and I write my novel and I edit it, and then I come back and people can read it. However, there are variations on this. For example, jazz improvisation. Jazz improvisation, we start out with a common understanding, and then we're all experts. You don't want to get in a jazz trio with someone who just now is seeing a piano for the first time. It's awkward for everyone. So we all know our instruments, but also we know what the 12-bar blues is, or we know what, you know, the piece we're playing around. We know what an augmented chord is, or a diminished chord, or a transition. And so, but it's much, much narrower than a symphony. We can't, in real time, write a symphony. So even the best jazz, even the greatest jazz geniuses have to stick to a fundamentally narrower form, because it's a conversational form. There's only so many things you can do in real time, but you're free to do things that interact with a live human being who's looking at you. Similarly with acting. You can write a play and people present the play, or you can do improv. And improv is much narrower than any play that would be written by a playwright, because there are rules. If we're doing improv comedy and I tell Jesse, what's that chicken doing on your head? He's actually not allowed to say, I have no chicken on my head. He has to say, give me an excuse why there's a chicken on his head. And the reason that we do this is that you need a narrower scope for the real-time improvisation to be able to happen. And then you have this very, very free space within that. I think the same thing's going to happen here. A lot of stuff people will do in compositional time, but then there'll be other things that we don't yet think of as happening in conversational time that those compositional creations will be supporting. So for example, I'm talking to Jesse, and he sees this, and he sees that I drew this, and he says, you know, I have an idea. And drawing on the language, you saw the dictionary at the beginning, he says, I have an idea I think the shape should look more like this, and he scribbles a shape in the air, and he starts editing it, and he's making changes which in real time are changing my shape and giving it a different kind of form. And just so you know what's going on here, for those of you who are programmers, this is a JavaScript object, and that's a JavaScript object, and when I drew that arrow, what's happening is that I defined a closure, which will make sense to JavaScript programmers. To everyone else, it's kind of a recipe for how to do things plus some data wrapped into the recipe. And so that recipe goes across to here. And what this is thinking of as a recipe to draw this is a different program. So it's thinking of as a recipe to make a solid shape with that as the radius. So a program gets put inside another program, and the containing program says, oh, this is just what I needed. You're telling me what the radius is as I create myself. So two different programs running here communicating through code. But now I might, so Jesse had this cool idea for a shape, but I might look at his shape. Remember, it's a conversation, and I might say, you know, I like that. But actually, I like the thing that you made more for a different reason, because I've been working on an animated character, and I think what you've just done is you've created what's a really cool path for that character. So maybe I want the character to go in a loop, and I say, why don't we send that same set of instructions over to my character, and now suddenly I have a character that's kind of like flying through the air or swimming or whatever, and we're doing this real-time changes. And again, it's a real-time collaboration. It's not completely magic in the sense that we had to have the vocabulary beforehand. I mean, I say the word elephant and you think of elephant. I say the word giraffe and you think of giraffe, but I can't just create a new word in the middle of the conversation. And you know what I mean by giraffe because you learned the word. And I think, and the same thing with syntax and grammar and semantics and all of these things. So I think that I want to just talk a little about, you know, in general, this idea that objects are things and symbols that describe the things. Like we all know what a light bulb is. A light bulb, but what is a light bulb? We can talk about what we do with a light bulb and demonstrate it for people. A light bulb is basically a transducer. It turns electricity into light, you know, and you can change the colors and all kinds of things, you know, and various things like that. But ultimately, that's what it's about. But now, suppose I wanted to tell a more sophisticated story with a light bulb. Suppose I want to talk about a light bulb as part of an Internet of Things. Like, oh, where we want to be eco-conscious, we don't want the light to be there unless blah, blah, blah. I want easier ways of turning it on, so maybe we apply a motion detector to it. Well, I can talk about, you know, here's an object, and that object is a camera, and this camera is looking for changes, and then we connect that camera to the light bulb. And this, by the way, this is the only part of the talk, I confess, this is the only part of the talk that actually is going to involve hand waving. So if I wave my hand in front of this, then light bulb goes on, light bulb goes off. And what's really going on is that this is a code object. It has code behind it, and it knows about objects going in front of it, and it basically can react to objects going in front of it by turning on and turning off. And so really behind all these things is programming. So just you know, none of it's actually completely magic. It just seems like magic because the programs all work together. And I want to show you a slightly more sophisticated example now of one that there was a topic in my computer graphics class that I was never actually able to teach effectively because it was just too abstract for people. And it's one of the core topics. And so finally, you know, I would try it on blackboards, I would try running programs and doing demos, and I never quite, and that's the, but now I think I can do it well because I have a tool like this. And in the future, we'll be able to gather around in a circle, and I'll be able to do it right in front of people because we'll all just be wearing the glasses. So, and that's the problem of how do you make transformations inside coordinate systems. So, you know, at first we think of coordinate, when we were kids, we learn that computer graphics or coordinate systems are two-dimensional, but we get older and learn they're really three-dimensional, okay? So if you want to describe reality, you need that third dimension, Z. And so in some sense, the coordinate system is a picture frame for describing things, but it's a three-dimensional picture frame. When I was a little kid, there was a cartoon called Tennessee Tuxedo, and I don't know if anybody here has ever heard of this, but it was, I have no idea if it ever got to France, but it was, he was a cartoon penguin, and he and his friend Chumley, who was a walrus, of course, they would go to their friend, Professor Whoopi was his name, and he was their friend, the scientist. And he would explain things to them when like, oh, how does television work? Or how does rain work? And this was part of a movement that that children's television should be educational. So they'd like slip in like some kind of lecture. But he had what he called his 3DBB, his three-dimensional blackboard. And he'd take it out of his pocket and he'd go like this, and like this. And it was that third thing that was amazing, the third movement. It's like, and then suddenly it would cut to some like cool animated explanation of some topic in physics or science or something. And I liked the topics, but I wanted that 3DBB. So in some sense, I think what I'm doing is kind of approximating, like, see, who says television is bad for you? So here's an object, right? And it's just a simple shape. And any property of this shape, of course, is going to get replicated in the view inside this. If I change the shape, if I modify it in any way, then you see that change in the view. So you could think of this as a kind of a funny kind of camera. But then if the topic in computer graphics that I'm talking about is how do you transform things, well, we can see the object untransformed, and then we can see what happens after it's transformed. The difficult part is explaining the math to do the transformation. And it turns out that that math is the way we represent linear operations, rotations, translations, scales, which is with a 4x4 matrix. So these matrices have a particular structure. They're basically X, Y, Z go in, different X, Y, Z go out. And so the way the matrix is structured is that the right-hand column of it controls translation for moving things. If you want to rotate something about the X-axis, then x doesn't change, right? If I'm rotating about the x-axis, x doesn't change. But y and z kind of flip with each other, right? Does everyone see that? So, so that's why the matrix has to look like that. Because the x-axis, the first one, doesn't change. But the y and z is this like sine and cosine action going on. Can you guys see that? I can make it bigger if it's, there you go, okay, a little bigger, okay. So now, this isn't just the idea, like in a textbook, of sine and cosine. You can actually say, hey, why don't we just take actual values and stick them in and change them? And so now it's because I've got a little slider, and I'm changing sine and cosine. And this object, because it's a visual language, this object, it's a matrix, it's a noun, but it's also a verb, because objects can do things in a visual language. So I can pick this thing up, and I can drop it in the relationship between these two other objects, and now you can start seeing this. In fact, I think I need a bigger scale there, right? So now you can start seeing that, can you see that? Oh man, all right, I have to make a different color. I just looked over there and realized that you can't actually see that color on this projector. How about now? Is it visible? Can you see the object? Okay. Yeah, it's very frustrating because it's perfectly clear here. But, I'm not sure I agree with Jesse. I think I'm much less interesting to look at than what's happening there. But then, for example, you say, oh, I see. So if I rotate about the x-axis, the object tumbles this way. If I rotate about the y-axis, the object tumbles in a different way. You know, you can see it's now rotating about that. I think I'll just make it white because I think it's the only color that's going to be really clearly visible to you. Okay, bless you. But meanwhile, because it's a visual language and everything has a relationship to everything else, I can introduce another concept. I can say, well, why don't we just introduce time? This is how I choose to represent time. And so now the relationship between the value and the matrix changes, and now I'm just controlling the rate, and I can say this is rotating about y, rotate about z, etc. And so a topic which I could have spent an entire hour on, and people are like, well, what is that? What is that? How does that relate to that? And all that suddenly is something I can explain to people in a few minutes, and they really have an operational knowledge of it, and then they can go off and program, and the math is clear in their heads, and they can just deal with turning the math into programming as opposed to, because once you start doing graphics and you don't understand the math, it doesn't matter how good a programmer you are, you're not going to get anything done. So it's getting the computer graphics is really about math and pictures, and the computer is just plumbing. The programming is just the thing that gets you to connect the math and the pictures, but the real interesting topics are the math and the pictures in computer graphics. So this is all very interesting, but for me, what's more interesting, oh, by the way, I should mention that all of this stuff runs on phones. This is actually, this stuff is actually all 3D. You know, this is a 3D object, rotates in 3D. And I can rotate the whole view. You know, when you run it on phones, because it's just HTML, so I can write my own little shaders. So it's stereo. So, and in fact, we could have all sorts of fancy objects in this. It's a little gallery of 3D objects that, you know, you can rotate around. And again, they're all run in stereo. So you can create entire worlds, but stylistically, I'm really interested in exploring this very, very simple world of the sort of the cave paintings, slightly updated. The last thing I want to talk about, because it's really the subject that's really near and dear to my heart, is this idea that when Jesse and I are having this conversation in the future, one of the things that we're going to be able to do is just make our creatures. So, you know, we make some gesture and we draw something, and because we draw it, this computer knows what it is. It comes to life. You know, it has behavior. This, by the way, came out of I once met Randall Munroe, who some of you might know is the author of XKCD. And it's like funny because I've met all sorts of famous people, but this was like my only total like tongue-tied fanboy moment. Like I'm talking to the guy who does XKCD. He's a real person, and I try to act normal, act cool. I asked him for advice, and he said, make the drawing simple as you can. And so I took his advice. But the thing is that you can give behavior to these things, you know, and they respond, you know, and because there's a computer program running, so it's not just trying to get somewhere, nowhere fast. But this notion that I can draw something and it becomes a thing that's there, and then it starts having behavior and personality, and how I draw it can influence. So, for example, you know, if I draw I can draw some kind of creature, and if I draw it like with short, stubby legs or something, you know, it'll walk really slowly. You know, maybe if I draw it like with really big legs or something, I don't know. Let's try drawing it with like really big legs and see what happens. The computer looks at how I drew it and says, okay, you drew it like that, therefore you want it to have a different personality. And I think it's this notion that the customization of the drawing, the fact that I draw something and you draw it differently, just as we speak with different emphasis, you know, we choose to arrange our sentences slightly differently, and it's that subtle shading of meaning. If it always drew exactly the same thing every time I look up something in the visual dictionary, that would be boring. That would be reducing expression. But we need to keep those many dimensions of how we draw things. But ultimately, I'm just really interested in this kind of thing. I'm interested in these characters because, as I said toward the beginning of the talk, the most interesting thing about these characters is not that we're interested in them. I think it's that they're interested in us. And I think that's what kind of drives us, is we want that little toy dinosaur to turn and look at us. And now, of course, they can. So here, this guy here is really fascinated by my cursor. And there's a reason he's fascinated by the cursor. He's fascinated by the cursor, it turns out, because he's actually very ticklish. And that makes him very happy. But eventually, he leaves us anyway. And I think that might be a good place to take questions. Thank you.